Okay, so bridge specification, for example, whenever you will go to design any bridge, you will see this document. And this document is revised in every 5 year, 10 year, 15 year or 20 year. Okay, I will share this document with you and you would be surprised that this document has around 1500 pages. Okay, around 1436 pages. So just imagine how much would be the thickness, something about this much. Because 500, you have a 500 rim, 500 pages rim. So 3 rims together. So this is the thickness of this document if you print this document. So this document, AASHTO LRFT bridge design specification, we have 2 types of bridge designs. One is allowable stress and one is LRFT. So what is the difference between AST and LRFT? Have you studied these 2 design methods, ASD? I taught in reinforced concrete design there are 2 design methods. One is ASD, allowable stress design, and one is LRFD, load and resistance factor design. What you have studied in steel design or in concrete design is LRFD or strength design. We also call LRFD design method as strength design method. In strength design method, we have the major factor of safety on loads. You can apply factor of safety on the material and you can apply the factor of safety on the load. For example, if the material strength is 300 megapascal, you consider 200. So what you did, you apply a factor of safety. Do you understand? In case of material, you reduce material strength, and in case of loads, you increase the loads. But in case of strength design, we have 2 factor of safety. The one factor of safety we apply on the material, the other factor of safety we apply on the loads. For example, if you remember the reinforced concrete design, there is a phi factor. If you calculate the capacity of any moment capacity or nominal capacity of flexure, shear or compression, there is a phi factor. Do you remember?
Yeah, direction factor.
Phi reduction factor 0.9 for flexure, for shear 0.75. What is that phi factor? That is a factor of safety. That is, for example, the actual strength is 100, you multiply it by 0.9 and you say it is 90. So you reduce it. The actual strength is 100, nominal, Mn, but you multiply by 0.9 and you say the required the strength of the section is 90. So 10 kilonewton meter is the factor of safety. On the other side, you multiply by dead loads by 1.6 and dead loads by 1.2 and live loads by 1.6 to get WU. So that 1.2 plus 1.6 is a factor of safety on load. So what you do, you apply the factor of safety on material and you apply the factor of safety on the load. You have 2 factor of safety. So in case of load and resistance factor design, again we have 2 factor of safeties. Okay. Now let's move next. This code is developed by American Association of State Highways and Transportation Officials, and so if you see, this code discuss about what? Number 1, introduction. Number 2, general design and location features, load and load factors, structural analysis and evaluation, concrete structures, steel, aluminium, wood, decks and deck systems, foundation, abutments, piers and walls, buried structures and tunnels, railings, joints and bearing, almost every aspect of a bridge design. But you know what? The first part, introduction, I think I have almost done with that. I will not spend any time on it. General design and location features. Location features also I discussed very briefly in my previous class. So the third part, loads and load factor and structural analysis and evaluation. Concrete structures, steel structures. So 3, 4, 5, 6. In this course, mainly we will be talking about 3, 4, 5 and 6. Loads and load factors. Okay. So, for example, like decks, you know what is deck I told you?
Yes.
And also you know piers.
Yeah.
Foundations and walls. Body structure and tunnels, they are not in our scope. And railings. What are the railings? Railings.
Railway.
No. On the sides of the bridges, we have some steel or concrete. Steel railings to prevent the truck or car to fall down on the other side of the bridge. So those are known as railings. Let me see. I think you know that. There's no need to show you. Okay, so as I told you, this class is just to expose you with this AASHTO code so that later on if someone asks you what is AASHTO or have you seen AASHTO anytime, anywhere in your life, you can say yes. We have studied, we know this. And introduction. This is the introduction. In the introduction, there are different definitions like what is a bridge. So this is a technical definition of a bridge. Any structure having opening more than 6.1 meter and that is a part of highway located over or under the highway is known as bridge. Do you understand? So in a road or on a highway, if there is any gap which is more than 6.1 meter and you try to cover that gap, that is known as bridge. Collapse, design lab. What is an engineer? Who is the engineer? Person who is responsible for design of the bridge and review of design related field submittals such as erection, plans, construction, fabrication is known as engineer.
So, if the gap is less than 6.1 to call culvert.
Yes, you can call it as a culvert if that is used for water. Yeah. I think there should be somewhere culvert. It's not text, unfortunately. Okay. So design philosophy. Design philosophy. This is a chapter. Is it clear to you now?
Yes.
No. So this is the limit state. This is the main design equation for a bridge, this equation. This equation is the main design equation for a bridge. For example, all limit states shall be considered of equal importance and that is equal to this. It is a general equation. For example, what is R? R, this one, capital R to small r, it is the required load. It is the required load. And what is Rn? Rn is the capacity. What is Rn? Capacity. And what is Ni? Ni is basically Nd, Nr or Nl. So what are these factors? This is the main design equation. I want to show you, this is the design philosophy, limit state design. And this resistance factor is 1 for all non-strength limit states. What is a limit state? For example, there is a bending limit state. There is a shearing limit state. There is a flexure limit state. There are different limit states which we are going to study. And these are the different factors. What is ND? ND is ductility factor. And its value is like here for 1 for conventional design, 0.9 for connections, and 1.05 for non-ductile components. But for all other limit states, you can take ND equal to 1. And then it is ductility. This is ductility. There is no need to. What is ductility? The deformation at ultimate divided by the deformation at elastic limit is known as ductility. Have you heard this word before, ductility?
Yes.
Ductility. So this is the definition of ductility. For example, if you have a steel rod. You apply a tension test. So there is one point which is known as yield point. Before yield point, the steel is elastic.
And after that, it will become plastic.
And after that, it will become plastic. And there will be a point at which it will break.
Yes.
For example, if you elongate it, for example, failure. So this delta U is the displacement at failure. And this delta Y is the displacement at yield point, because before yield point it is elastic. So if you take this ratio, it is basically ductility.
Because it can return to its original shape.
Yes. So this is NR. This is redundancy factor. What is redundancy? Because in bridges, the structure is not that simple. There are many supports, many extra members, many components. So for example, if the wheel is there, then the member here is redundant. Redundant means of no use. So we have some redundancy factors which we consider in our design. One is ductility factor, redundancy factor, and then we have the next one is NL. This is operational importance. For example, how important is your bridge? Is your bridge going to be used for a military purpose? Is it a normal pedestrian bridge, or it is used for an important highway? So this factor actually determines the. I cannot use it. So you are very late today. Very bad habit. It's from structural analysis. You're taking third course with me, I think.
Yes.
Yeah, and right from structural analysis, you are always late in the class. Just 1 minute. No, my laptop is very old. It is some it's very old, so I cannot connect 3 or 4 devices together. So when I connected my mouse, it stopped working. The Acrobat. Just 1 minute. So we were discussing about different factors. Have you studied ACI code in your class?
Yes, I call.
Have you?
I don't think so.
Yes. ACI code. Have you ever heard about this?
I heard about it. It's American Concrete Institution.
Okay. I remember I taught this in the class. Okay, so this is AASHTO specification we were discussing. Something happened. It is not a takeoff, it is a voice of mine. No, there is no takeoff aeroplane right now. Many people they ask about that what is pre-stressing? Pre-stressing. And in the new design codes, now we have the bridges which are, the bridge designs in which there is pre-stressing and post-tensioning. So it is really an interesting thing if you can arrange a field trip and we can go and see the pre-stressing. If you know some bridge construction is happening nearby, we can go by ourselves and we can see the pre-stressing or post-tensioning. Any one of you? So we were discussing about some redundancy. For example, there are three factors I told you. One is ductility factor, one is redundancy factor, and one is NL operational importance factor. So these are the three factors which are used here in this equation. In this equation, you can see here. So it should be greater than or equal to 0.95. The minimum value is 0.95. For most of the cases, in order to avoid all these problems, we take it equal to 1. We also take it equal to 1 for simplification purposes. For example, this is all about the ductility, redundancy, and operational importance. Yeah, that's all. This is the chapter 1. And then you don't have to remember anything. It is just for your understanding. General design and location features. For example, how you can decide the suitable location, route location. So it is given here. Some of the points, for example, like if there are waterways and floodplain crossings, what we should consider, bridge site arrangement, how you should arrange, traffic safety, protection of structures, geometric standards, road surfaces. So there are many things which are like clearances, navigational, highway vertical clearance, horizontal, railroad overpass. So these are general serviceability and durability. What is durability?
It's about how many years.
How long it can sustain.
Yeah.
Okay. So what are the durability factors you can study here in this code? Inspectability. How long you should inspect. Where you should put the inspection ladders. Inspection ladders, walkways. For example, in the box cutter on the bridges, we should put something so that we can go there, we can inspect. There are some cracks, and if we want to measure the vibrations, so it should be accessible. Reliability, utilities, deformations, And then I quickly want to go to the next chapter. Yes. This is the minimum depth for slabs. If you see this, what is superstructure? I told you
So
last
it's
time.
High set weight.
The structure of the bridge above bearing is known as superstructure, and the structure of the bridge below bearing is known as substructure. So what is this? Traditional minimum depths for constant depth superstructure. For example, in superstructure, what do you have? Slab. The main slab. How you find the thickness of slab? By this formula. (1.2) plus 3000 over 30. What is S? S is the spacing of girders. For example, in a slab bridge, first if there is some section here, I think there will be no section here. Can you turn on this? Just by the okay. So what is it? Now please see here. Then we have this is one carriageway of a bridge, and then you have girders. These girders could be rectangular, these girders could be I or T. Okay, these are the girders. So what is S? S is the distance from center to the center. For example, if you have 4 girders, you can find this S, and once you have S, you can put the value of S in that equation and you will get the thickness. Now this is the cross section of a bridge. Sometimes we have the walkways. Sometimes we have the, it's very difficult to erase it, you know. Sometimes we have walkways like this. On one side we have the walkways. It's very hard to remove it. So in this formula, if you see, what is S? The spacing of the girder. Simple spans, what does it mean, simple spans? For example, in this case, if there are 2 girders and the slab is just like this, so this is a span of slab. Okay, this is a simple span. Or in that case, if you put one slab like this another slab, third slab. So I mean, there is no continuity.
Yeah. Separate.
Separated. So then these spans are known as
Simple.
simple spans. But in most of the cases we have the continuous. So if we have like this, a continuous span, then we will use this equation on the right side to find out the. For example, if this spacing is like 2 meter, how much will be the thickness of slab?
We just put in this part.
Or if the girder spacing is 3 meter, it is how much? It is 2 meter.
Yeah.
You just put 2 meter into this. This table is very important. We will use this table in our design. That's why I'm spending time on this
2
table.
meters in millimeter, right?
Sorry?
Millimeters, 2000.
Yes. It will be 5,000 over 30.
200.
Multiply 1.2.
100 millimeters.
After multiplying by 1.2?
Yeah.
Yeah.
And divided.
So it should be 200 this much thick slab. Just see. 20 centi. So get an idea. This is a thickness of a bridge slab.
So for continuous slab, it is should be less or equal to 165.
Greater. The minimum thickness is 165.
How about simple span? Okay.
Yeah. For that, for simple span,
Biologic, I think.
no. The simple span will always be greater than this one. The simple span, okay, check the same 2 meter for the continuous. Simple span is always greater than the
Will be
continuous
less
one.
because there is no point.
5,000 over there. Oh, okay, I calculated the simple span. Yeah,
Of course, it will be great
yeah.
because
The simple span is 200.
So do you understand?
Yeah.
So it should always be greater than that. Yeah, because it's the same formula. So in simple span we have more than
It's the continuous, 166.
166.
Yeah.
Okay, fine. But this is the minimum thickness. We should not provide less than 165 mm. Okay. T-beam. For example, in this case, our girder is not connected. But it's
Separate.
separate. Sometimes for example, if I'm worried who will erase it. In this case, girder is a part of bridge slab. Have you studied T-beam in reinforced concrete design?
Yes.
Yes.
Yeah. So it means now in this case it is what? It is like a T-beam. So in that case, how to find out the depth of T-beam? Depth of T-beam, this depth. How you can find out?
The beam.
The length of the beam multiplied by this. This is T-beam. And what is this? This is box beam. Yes. And then we are talking about normal reinforced concrete bridges. If it is a pre-stress, then you can use this formula. If it is a steel bridge, then you can use, everything is same. If you know L, you can find out what is L. L is the span of the girder. L is the span of the girder and S is the spacing of the girders. Okay? So this table is very important.